Okay, so please, Elif.
Okay. Hi again. The next speaker is Yiğithan from Middle East Technical University. We studied together an extension of type theory called Homotopy Type Theory, which is my personal research area. For me, understanding the basics took months, but he grasped many ideas in a couple of weeks. It was great. I hope you all enjoyed the content as we did. Okay.
Thank you, Elif. And I'd like to thank you for your time and patience. I was a bit lazy at times, and I also like to thank the organizers for giving me this opportunity. I'd also like to thank Praneeth and Mr. Voss and Bhop for their many suggestions. So this is a fleeting glimpse of Commodities type theory. Now, quick remark: most people brief that as homotopy, but I think that sounds sort of funny, so it's homotopy, but don't be confused with something. So this is our table of contents, but I don't want to lose any time because we have a lot to cover. So let's just get started. So homotopy type theory, or Homotopy type theory, is a type theory that puts special emphasis on higher categorical structure, right? So homotopy structure. And it's designed to, be a foundation of mathematics, unlike set theory, which was initially, like set theory initially started to, scrutinize the infinite, and then it later was adapted as a foundation. And so there is no unified homotopy type theory, so it might refer to a number of things. So we will develop a homotopy type theory based on what is called intentional intuitionistic type theory of Martin. So I'll just say MLT, MLTT. So that's Martin type theory, and we'll basically do everything HOT, like the same way HOT equals. And like there are alternative ways to build a homotopy type theory, and you can look up cubical type theory. So how many of you know what a homotopy is? That's great. Okay, so I should probably drop some. So let's suppose we have can the camera see here? Is that fine? So there are two different notions. Actually, I'm going to introduce three different notions. So first is homotopies of functions, continuous functions. So suppose we have some topological space X and Y, and we have two functions from here to here. So this is the image, and a homotopy basically deforms this into that continuous. And you can see the definition, the formal definition. I'm not going to get into it. So we will treat homotopies as higher paths. So I'll get to that in a second. So there's also the notion of homotopies of paths. So you can have two paths. I'm assuming everybody knows what a path on a logical space is. So you have a path, you have another path, and if their start points and end points are the same, then you can continuously deform one into the other, then we're gonna say that they're homotopy. And homotopy between paths is like a higher path between them. So you can have a homotopy between paths, or homotopy between just homotopies and so on. So there's hierarchy of paths, sort of. And this is an important idea in homotopy theory and homotopy theory as well. And so we have the notion of homotopy equivalence of two spaces. So the idea is, so if you have two topological spaces X and Y, and you have one going this way, one going this way, and when you compose, you don't necessarily get the identity, but you want to get something homotopy to the identity. So so in a sense, it's up to a higher path, right? So so this notion of equivalence of spaces is up to a higher path, up to a homotopy. And these need not be bijections, so it's a weaker notion than a homeomorphism. So the standard example here is it's actually an ideal example, nice exercise to do yourself. So you can see how real numbers and a point are actually homotopy equivalent, and it's not that. So I'd like to thank Eren for introducing some types in Martinov type theory, but I'll briefly go over them as well. So we have a universe, right? So a member of the universe we'll call a type, and we're gonna say it contains all types, but there's obviously foundational problems that comes with it. we're not gonna bother solving them. Right, okay, so. Okay. So we have a type of functions from a type to another type, and that's pretty self-explanatory. So you can apply an element of the type, and then we have what is called a type family, and that's just a function from a type to the universal type. So basically, whenever you apply something here, you get a type. And so we have dependent functions, which is just basically the resultant objects when you apply something need not be of the same type. So like the type depends on the actual member of A used here. And so we have product types, which you can think of pairs, and we have dependent pairs. So these are given by shown by sigma, and again like dependent functions, like the type of this element right here actually depends on A. And so we have this this translation between new interpretations, right? So all in all, we have introduced symbols and like some meaning behind it, but there's another way to look at it. So you can look at things as a proposition. So for example, this means like for all A in A, P of A holds, and this means like if A holds, then B holds, and so on. But we're gonna introduce something called the homotopy interpretation, which basically lies at the heart of homotopy theory. So instead of saying A is a type, we say A is a space. So every type is basically a space, and every element of a type is not basically an element of this type, but more rather like a point on the space, right? And if you have a function between types as a continuous function, and a type family, it corresponds to something called a fibration, which I'm going to introduce in a bit. And we're going to have a couple more things, but I want to focus on this. So in Markov type theory, there's this thing called the identity type. So it's a bit mysterious. So you can think of it as like an element of this type is a proof that A and B are the same in the proposition explanation of it. But in the homotopy interpretation, this is just like this is a type from a type consisting of paths from point A to point B, and T here is just a path, right? You know how you can build basic geometry using like coordinatization, but you can also do it the same way Euclid did, right? So Euclid did not coordinatize it. He did not tell you what a line or a point is. He just used, he did things synthetically. Now, homotopy type theory, using this interpretation, allows us to, do the same thing, like do the homologous, analogous thing with homotopy theory. So we can talk about spaces, points, fibrations, continuous functions. Although we can't talk about, open sets, and also only the homotopy theoretic notion is preserved. Like no open sets. Right, so we all know natural numbers, and we all know the induction on natural numbers. So in homotopy type theory and in Markov type theory in general, we basically generalize that notion. So we have what is called an induction principle. I'm not going to go over that one for time constraints. So we have an element of this type, right? And this is basically what it says. So consider C here like a property of types. So you plug something in, you get like a proposition, right? So this is telling you exactly what you need to supply to get a proof for all n. So this says for all n, C of n holds. So you have to provide it a proof that C of 0 holds, and given a proof of C of n, you have to prove that C of n plus 1 holds. So this is basically induction principle that we know. But we can also look at this type family as like literal types, but not properties. So this also justifies recursive definitions. So you define something for 0, you define something given the nth term, you define n plus first term using the nth term, and you basically define it for the whole thing. Now, why did I tell you about all this? By the way, there are some coherence rules and stuff like that. So why did I tell you all this? Well, we're going to generalize this. So, and many types many types introduced before are primarily used using their inductive principles, right? And they characterize maps out of a certain type. So remember, this is basically a map from natural numbers to this type family. So we want to characterize, we want to know what it takes to build a map out of that type. So that's induction. And let's talk about the identity type for a bit. I've already introduced it, so it's like a type of in the homotopy interpretation, it's like a path of space of paths, right? So in Martin type theory, before the homotopy interpretation, it's sort of mysterious because it has a very weird inductive principle. It's also inductive type. But yeah, so we have a type of paths from A to B, like space of paths from A. And so one thing, so for each A, we have, well, this is a space of paths from a point to itself. And this referral thing here, like it exists for each A. And this referral thing is basically the constant path. So that's what you should think. Yes, and we have an inductive principle, but this is confusing. And I have not much time, so I'll just tell you what it means. So you have a type family, and this is basically telling you that, hey, okay, if you want to construct a function out of the identity type, so you should give me the values on the constant path. Or rather, looking at it like propositions, it is telling you that it is enough to prove some things like a property on constant paths to prove it for basically all paths on the space. And it's kind of interesting, but the homotopy interpretation gives us this much easier to understand V1s, right? So this is extremely important. Basically, every theorem that involves equality will use this one way or the other. And just a small note, in Martin type theory, there are two distinct built-in notions of equality, right? So we have what is called the judgmental equality. You may think of it as things holding because of their, things that hold because of their definitions, things that are equal because of their definitions. So it's sort of meta-theoretic. It's not the same equality that we saw before. The equality we saw a minute ago was the propositional equality. So that's the space of paths. Of course, if two things are judgmentally equal, that basically means that the two things are the names for the same object. And if two things are the names for the same object, then there's a referral term, so like the constant path between them. So you can place a referral term if two things are judgmentally equal. So judgmentally equality sort of implies propositional equality. But this is not that important. But just realize what this symbol means. It means judgmental equality. Now there will be other notions of equivalence we're going to scrutinize, but we will define them. They're not built into Martin type theory or homotopy type. Okay, a fibration. In homotopy theory, a fibration is basically okay. So it has many different. I can't write that. So it has many different definitions, but the most common thing in all those definitions is sort of the lifting property. And so the most common principle is that you can lift paths. So I'm going to give you an example of fibration. So suppose you have S1, right? The circle. And let's have a fibration. So it goes like this. Whoop. It comes back. Oh, that's horrible. Oh no, that's horrible. Apologize. Yes. No. You're gonna have to do with it. So it travels whoop, whoop, and comes back. And there's this map. So whenever there's a path on this, so suppose we have a path here, you can lift this, meaning that if you take the image under P, it will be on the same place. So that's basically what a fibration is. So you can lift paths basically, right? And well, in the homotopy interpretation, that's basically type family. So if you have a type family, that sort of means that, well, it's a function from A to U, right? So for each point on the space, you have like a fiber, and they all form this type family, which is the fibration. And this right here, the space up top, is called the total space, and this is called the base space, right? So the base space is A, and the total space basically corresponds to the dependent pair type. And if you wonder why, you can think about it. But know that there is, well, there's this lemma which says that you can lift types. So this is basically justification for why we think of this type family as a fibration. Now, a section is basically a map from the base space to the total space, so that when you go up and down, you land at the same place. I'm not going to draw one here, but that's basically a section. So a section actually corresponds to, I'll draw it. So you have a base space, you have a total space. This is like fibration with this P, and well, this is sort of a section. So when you, this map is a section, and when you compose it with P, you get the same place. So it's like a left inverse to P, if I'm not mistaken. And that's basically what it corresponds to in the Homotopy interpretation. That's basically dependent pi type. So dependent function type. And the reason is, well, for every point on the base space, you assign it an element of the fiber, and that's precisely what this means. So, okay, I said we can talk about homotopy theory synthetically, like the same way Euclid proved theorems of geometry without actually getting his hands dirty with coordinates. So let's see an example. So this is a very well-known theorem due to Ekman and Hilton. And so the second homotopy group is always sub U. Now, we need to first express this as a proposition. And well, in type theory, propositions are types, right? So we're gonna I'm gonna show you how you can build a type that corresponds to this. And so we define this loop space, which is basically a space of paths from a point to itself. And this actually this corresponds to, in homotopy theory, this corresponds to a subset of a to the I, like the a to the I with the compact open topology. It corresponds to as a subspace there, yes. So it's called a loop space, and we can take another loop space of it. So this will more or less correspond to the second homotopy group. And well, you can define a composition operation, like it's not that difficult, and we can basically say that this is commutative. And I mean, you can work this, like you can work on this, and you can convert it to a type. It's not that difficult. So this is how we speak of this second homotopy group in homotopy type theory. Now, the result is not immediate, but it's very easy. So you use path induction, like, I don't know, 5 times, 10 times, something like that. So yeah, I'm not going to talk about this in detail, but so we can logically describe spaces, right? Like we've described what a fibration is. So you can, like, given a space, you can look at its vibrations and so on. But we can actually describe more. So we can inductively describe like the S1, the circle, the same way we define I don't know, other types. So S1 is a type. It's basically the type generated by these. And like the key thing in this principle is, again, it basically tells you how you can build functions out of S1. And using this principle, we can prove properties thereof. Right, so a homotopy between two sections. So think of it like this. So we have maps, and like on the image, think of it like we're drawing like a path. Maybe I should draw myself. This is a mistake. I'm too much thing, but like, so suppose this is F, this is G, and at each point you are supplying a path between them. So this is like F of A, this is G of A, right? And at each point you are supplying a path between them. This is basically what it is. So a path between F of A and G of A. And if you have an element of this type, then you basically have a homotopy from F. Now, two things to okay, we're gonna introduce the equality of equivalence of types, but what is an equivalence? Well, so it goes from a type to another type, and well, there are maps going from B to A, the other way around, such that when you compose, you get something homotopic to the identity, not necessarily equal. So remember, this is what I talked about in the beginning, right? So equivalence of spaces is up to a higher path, so up to a second level path. So this is what's happening over here. And we define this the type of equivalences between types like this. So this means for each f, you get like no, like this is the set of all pairs where f is like function from A to B. And the second thing is a proof that it's an equivalence. So basically it's like a subtype. You can think of this like a subtype. And right, so now the univalence axiom, again, this is mostly like I've heard it being pronounced like univalence mostly, but to me it sounds strange, so I'll just say univalence. So you have two types and you can build a function. This is not that difficult to show. Like from the equality type to the type of equivalences. So it basically maps each like equality to the each proof of equality to a proof of. Now there's this thing that we use in homotopy type theory called the univalence axiom, which basically says that like this thing, like this a map that goes from here to here is itself an equivalence. So let's all take a moment to admire that. Done? Okay. Well, it basically tells you that equivalent types can be identified. So that's more or less what you've been doing like for years at this point, and what mathematicians have been doing for centuries. So two things are isomorphic or equivalent, then they're basically the same, right? And this is basically saying that, like, in a sense. And there are many consequences to univalence. Univalence is univalent foundations is a field of study on its own. But here are some of them. So you can use univalence to show that the fundamental group of the circle is Z. Now you have function extensionality that comes from univalence. So using univalence, you can prove that. So if functions take the same value everywhere, then they're the same, right? That's function extensionality. We automatically have that in set theory. Now, couple of words. I have to say a couple of words about constructivity. So Martin-Lev type theory is inherently intuitionistic, uses intuitionistic logic. So it's somewhat constructive, and you don't have a law of excluded middle. And you can add law of excluded middle to Martin-Lev type theory, but after taking univalence, you can't add law of excluded middle. It becomes inconsistent. So you might say, hey, like maybe I don't want to do constructive mathematics. So there's a way to work around that. So what you do is you stop treating all types like propositions. You only treat some types as propositions, and you put law of excluded middle on those types. So that sort of works. And in this sense, you can sort of embed certain types of set theory into homotopy type theory. Now, I'm not an expert in that, so I'm not going to say anything. But just keep in mind that it's not exactly homotopy type theory is not exactly inherently unconstructed. It is constructive, but you can work around it somehow. Right. So this is this is something everybody should know. So most mathematicians and I think most mathematics students think that constructive mathematics means you can't do proofs by contradiction. So you can't assume towards the contrary, and you can't prove something. Well, you can prove something by assuming towards the contrary. So you cannot assume not A and prove that A is true by showing a contradiction. That doesn't take place in constructive mathematics. What takes place is, okay, I've read it wrong way around. Anyway, so classically what you do is you assume not A, you arrive at a contradiction, and you say, hey, then A is true, right? And that logical principle actually depends on double negation elimination or the law of excluded middle. And I've just told you that you can't have that in univalent foundations. So what you define not A, actually the negation of A like this. So this means, hey, if you have a proof of A, then you have a proof of the type which has no elements. Go figure, whatever. So you cannot assume not A and prove A, but what you can do in constructive mathematics is assuming A and proving not A by a contradiction. So that's fully constructive. There's no problem. So okay, I've arrived at the end of my talk, and I'm sure the mathematicians in this room who are sort of foundationally aware are very skeptical of this. So why should you leave set theory? Why should you learn this weird thing that has to do with homotopies and so on? So I'll give you some reasons why you might want to look at homotopy type theory. So one thing that's not listed here is it sort of preserves the inherent monopic structure. So if you work with higher categories or something that has to do with monopic structure, you homotopy type theory might work better for you. So like I said, in a sense, set theory lives inside HOTP. Actually, ETCS can be realized in HOTP. So that's elementary theory of category of sets, I believe. It's slightly weaker than ZFC. You can add an axiom, but you can look it up. I'm not sure about it. And so if you're doing homotopy theory by HOTP, you can talk synthetically about homotopy theory. So you can just, without constructing a homotopy, this gives you a purely logical and syntactic way to do homotopy theory. Now, set theory, obviously, set theory was invented long before computers were a thing. So most proof assistant implementations have been in a form of type theory. So if you're trying to formalize a theorem, I think you will find proof assistants that use some sort of Martin-Lipp type theory in HOTT much easier to work with. I don't think it works with set theory at all because it's not constructive set theory. So I don't know a word about infinity one topology, but if you do, good for you, because there's something called an internal language of topos, and HOTT is basically the internal language of infinity one topology. And maybe somebody amongst here can tell me what that means. And so this thing that we've been doing, right? Where we've been using bad notation. Well, we're no longer using bad notation with univalence, because if two things are equivalent, then you can identify them. So that's a minor thing. And so I followed mostly the univalent foundations. The HOTP book. So this is called the HOTP. It's available online. It's a great source. It's a great resource. I've also don't read Hatcher. I don't. Actually, this is much better textbook when it comes to algebraic topology, introductory algebraic topology, and obviously I've used the labyrinth that is called NLab. I think that's it. Yeah.
Okay. Any